Hello everyone, how are you doing? I hope everyone is doing good and great. I am Mahesh, your physics teacher, and you're watching me on SMR Online Physics. Today in this class I'm going to discuss about, yes, power of a lens and how to find the power of a combination of lenses, and also we are going to discuss about when two lenses are separated by a certain distance, how to really find the effective focal length of the combination of lenses. Okay, hope you have seen my previous videos on spherical surfaces and the lens maker's equation. If you haven't seen it, please do watch those videos and come back to it, alright, so that you understand better. So let's have a good time. So now we are going to discuss about the first concept of this class. What is power of a lens? Okay, we know lenses. We have discussed in details about lenses. So when I say power, we have studied about mechanical power. We have studied somewhere electrical power. But this power is of a lens. It actually expresses, my dear, the converging or the diverging ability of a lens. Alright, so how do we measure it quantitatively? Let's quickly see that. It's very easy and crispy. Alright, so let me have a good diagram and let's use a convex lens to understand the measure of its ability to converge, or if you're talking concave lens, the measure of its ability to diverge the incident beam of light rays. So this is your well-known converging lens. So let's quickly do that. This is your principal axis. Let's call it as optical center, as you all know that. So if the object is situated at infinity, then the light rays actually travel parallel to the principal axis. Yes. Now this ray of light, as you already know, doesn't really go straight. This is the intended straight path. It doesn't go that way. This lens, because of its unique shape and the differences in the optical densities of the medium, it bends the light rays, or we say in better words, it refracts the light rays onto a point. So let this be the point of convergence, and this will be called as the principal focus of the lens. The distance measured from the optical center to the focus, this distance is called as the focal length of the lens. That's it. So if this perpendicular height represents the height h, then we can easily see that, you can see that the light rays coming straighter do not really go straighter. They actually bend by a certain angle. So this is very appropriately called as the angle of deviation. Let us represent it by the Greek alphabet delta. So now it's all about geometry. We are talking about ray optics. So if this is your delta, then this angle also has to be your delta. Right. So we can take a measure of this delta as simple as this. From this right angled triangle, what we can easily see there. From there I find 10 delta should be equal to h by f. That's all good. We are dealing with thin lenses. You remember it, right? So if you put a condition like if h is equals to 1, that is unitary, then we can say the tangent of delta should be equal to 1 by f. And for very smaller angles of delta, tan delta is equivalent to delta. Okay, we have discussed in our previous classes also. So we can say for very small angles, tangent of delta can be written as delta equals to 1 by f. Means the angle by which the light rays actually get converged in case of a convex lens, and the angle by which the light rays will get diverged away from its intended incident ray direction is equal to the inverse of the focal length of the given lens. Hence we can say the power of a lens is the reciprocal of the focal length of the lens. As simple as that. That's it. But one good thing to be remembered is the focal length needs to be expressed in the units of meters. It is a requirement to fulfill. If focal length is expressed in meters, generally many people do not use the unit of power of a lens when we even go for a spectacle shop. We just give a unitary number and we give some signs like plus and minus. But actually internationally the power of a lens has got its unit. If focal length is measured in meters, then the SI unit of power of a lens is diopter. Is actually called diopters and denoted by capital D. I think you can see that, or if you wanted it, I can write it over here. The unit is diopters, denoted by capital D. That is the SI unit of power of a lens. So as you already know the sign conventions from our previous discussion also, for convex lenses, the sign convention for the focal length is positive. So hence, for convex lenses, F and P, if F is positive, P is also positive. Okay? And similarly, it's so easy to remember as a student, for concave lens, exactly should go the opposite way. The focal length is negative sign, so hence the power of a concave lens is also chosen to be negative. So definitely people do use concave and the convex lenses for correcting the defects of vision. So people with hypermetropia do use positive powered lenses, and people with myopia do use negative powered lenses. Alright, so that's it, my dear. As easy as that. P is equals to 1 by F in meters. Now if you tend to forget the focal length should be converted in meters when you're solving the problems, then you can always remember P is equal to 100 by F, provided again you don't convert it. Okay, then focal length can remain in centimeters, and you can just apply this formula, you get your right answers. But please mind it, you don't forget your signs also. Now we'll talk about what will happen if two lenses are really combined. If they are in contact, what would happen to the power of the lens? So now we will talk about the power of combination of lenses. How will the power change? Actually the answer is pretty simple. How the power actually adds up. It adds up along with the sign conventions. Let us see the mathematical derivation. Let us use now a concave lens, which is by nature a diverging lens, which has been combined with a convex lens. That's it. So both the lenses may have different powers also. So let us see how to really find it out. Let us call this lens as L1. This is my concave lens. Let us call the convex lens as L2. And this is the common principal axis passing right through their centers. This is my P1, this is my P2, the optical centers of the lenses. And let us say the lens L1 has focal length F1 and lens L2 has focal length F2. As simple. Right. Now let us see what exactly happens here. If I take in, this is the point object lying on the principal axis, a ray of light which is incident upon this concave lens by nature will start to diverge. Will diverge. You can see the small divergence has been shown to you in the diagram. This divergent ray when produced backwards meets somewhere else. So this is called as the virtual image of this point object. All good and great. But what will the convex lens do, my dear? It will always converge the light rays. So what happens here? The light rays start bending and they bend more. They bend more, and hence the light rays intersect at one common point, giving us the final image. Alright, so this distance measured from the second lens to the image, the actual real image formed, is our image distance V, and the actual object is this O, which was actually kept far away from this first lens. So this is my object distance U. All good and great? Is the diagram clear? Great. Now for this first initial object distance, the initial virtual image formed was O prime. Let us call it as V prime from the lens. That's it. Now what to do? Simply we have to calculate individually. So for the first lens, let me write here, for the first lens L1, which is in fact a concave lens, let us write down the lens formula. I hope everyone remembers what is the lens formula. If not, if you do not know exactly how to get to the derivation of the lens formula, then go back to our previous video titled Lens Maker's Equation. That's great. Come on. So the equation is 1 by V. 1 by V standing for image distance. So for the first lens, image distance is V prime minus the object distance is exactly the same, U, and its focal length we have chosen as a number F1. That's all good and great, right? Now similarly, write this same formula, keeping in mind all the conditions, the lens formula for convex lens. For this second lens, the object, the role of the object in fact is played by this image. The virtual image acts as an object for convex lens. So in place of image distance, this is the actual image formed for this convex lens. So image distance remains to be V minus, now here you should really be careful and apply your understanding. Here the object distance is V prime, not the U. I think you got it right. So here I should write V prime, and the focal length of this lens can be something else. Let us call it as F2. So if you take the first one as first equation and the second is the second equation so far we have generated, all we have to do is add these equations. Add equation 1 and 2. That's it. You will find 1 by V prime minus 1 by U plus 1 by V minus 1 by V prime equals 1 by F1 plus 1 by F2. So do not forget, you cannot forget, right? You remember what is the power of lens definition. So here you can easily see that you lose this term and you're left with 1 by V minus 1 by U equals 1 by F1 plus 1 by F2. So it means that these two lenses combinedly are playing the role of a single equivalent lens for whom the object distance will be U and for whom the image distance will remain as V. For that equivalent lens for these two, that single equivalent lens for these two will be having some focal length. Let us call it as 1 by F equals 1 by F1 plus 1 by F2. So the equivalent focal length for two lenses in combination will be equal to this. And from here you can easily see that the total power of the lens will be equal to a simple numerical addition of the individual powers. This is the total power of the combination of the lenses. So again I repeat, please do not forget to apply the sign conventions when you are using the power of the combination of lenses. If you are combining something like this, then for concave lens, if it is minus 5 diopters, please write here minus 5 diopters. For convex lens, plus 2 diopters here, minus 5 plus 2 diopters will give us a net result of minus 3 diopters. Means the combination of a concave and convex lens in that case will behave like a minus we got minus 3, so it should behave like a diverging lens of the net power of 3 diopters. I hope you're getting it all clear, right? So now we'll talk about two thin lenses separated by certain distance. Alright? So when two thin lenses are separated by certain distance, it's not same as what we did so far. Two lenses combined up. No. When they are separated by a certain distance, they do not behave as exactly one single lens. It's slightly complicated. So we'll deal it for a case, a very special case, as if the object is at infinity. When the object is at infinity, parallel beam of light is incident upon the lenses. And let us see what is the equivalent focal length for such a combination when two lenses are separated. This is going to help us a lot in our upcoming topics. Alright, please pay attention. I will do it in the crispiest way and make you understand and feel better. Right? So let us see how it all exactly happens. It all begins with a very neat, clean diagram. So take that point for seriously. Let us see, this is your first lens, a convex lens of certain focal length f1, all right, and certain distance away there is another convex lens and may have different focal length also. Now you can, this is what I mean to say, two thin lenses separated by a certain distance. So let us say the distance of separation between the two lenses is given by d. Alright, good. Now let us get this principal axis right through the lenses. We will need some space for doing the mathematical part also, right? So let us call this as the optical center P1. This is your optical center called P2. All good. So now, as I say, we will be solving it for a very special case as if the object is at infinity. So as the light ray comes in and strikes upon or being incident upon the first lens, this is your lens L1 and this is going to be a lens L2 having focal lengths, need not say f1 and f2. Alright. So this light ray, instead of going straight up, this is all geometry, very simple. Now it starts bending through and strikes over here. So it goes some bit, let us say something like this, and now instead of going straighter from here again, as I can show you that, this is the center of curvature for the surface, it actually bends down and finally there is the image formation. Alright. So it's all about picking up the deviation correctly, knowing the meaning of deviation. This is the first angle of deviation, delta 1, and let us say this height is h1, and from here let us say the deviation is delta 2. The deviation may not be exactly the same as you can see here, and if you want to find out the overall deviation done, you produce this final refracted ray backwards and straight. Yes. There you go, you find the overall deviation, let us call it as delta, okay? So here we can visualize as if the equivalent lengths of these two lenses will be lying around. So let us mark it with a dotted line. And let us say that equivalent length and optical center is marked as P. Alright, so let us see what we have. If this is delta 2, then vertical opposite angle, this is also delta 2. Now observe this geometry carefully. Let us put some names. This is X, this is your Y, this is your Z. This tiny distance is your H2, and if required we can use this. Let us call it as A. So from geometry of the diagram, from geometry, I write it very clear. I want you to be very, very crystal clear. This delta should be equal to the summation of delta 1 plus delta 2. Agreed? Is that all good? Right. So it has to be delta is equals to delta 1 plus delta 2. Let us call it as equation number 1. Now if you see individually for this lens the angle of deviation created is delta 1. And for this lens we have chosen the focal length is f1 and the height of this part, that is xp1, is h1. So we have just seen it, how to write the relation for delta 1. So we have individually delta 1 should be equal to h1 by f1. बहुत बढ़िया, ठीक है? And similarly for this second lens you can see delta 2, this is h2 and the focal length is f2. So we can write delta 2 should be equivalent to h2 by f2. And similarly for the equivalent lengths of this two, if the angle of deviation is delta, this is the same height h1, and let us call its focal length as capital F. So we should have delta equals to h1 by capital F. I think everything is crystal clear. अरे भाई कट गया वो तो. Not here, not here, not here. So let me write it here itself, and delta is equal to h1 by f. This part I am writing for the combination, the equivalent lengths of this two. Is that clear? Right. So it's very hot over here, so do not mind the sweaty part. Please focus on the beautiful derivation of this particular condition. Two thin lenses when they're separated by certain distance of d. All right. So we have this delta 1, delta 2, everything ready for us. So what we will do, we'll just put this masala into equation 1. That's it. So I should write it here. Now in equation 1, if I put everything in equation 1, delta should be coming up with h1 by f is equal to h1 by f1 plus h2 by f2. So what's our goal? Where are we moving towards? Our goal is to find the equivalent focal length of this combination of these two lenses separated by certain distance of d. So मुझे ये capital F को चाहिए था, ठीक है ना? So we have this h1, h1s, f1s. Let us find out how we can replace this h2. This is the tiny part h2. So we leave this equation over here. Let us call it as equation number 2. All right? So now we'll find out what is this h2, okay? Let's find out from the geometry of this part. You can easily see that now I shall write it quickly. h1 minus h2 होता है क्या? एक बार check कर ले फटाफट. This is your h1, this is your h2, so I will be left with this part that is equal to yz. So what is yz from the geometry? If you see carefully, yz forms a small, large, this long, elongated right angle triangle. So this is your perpendicular side, this is your base side, which is xy. We know the value of d, that xy is d. So I can easily write that should be equal to h1 minus h2 is equals to xy tangent of delta 1. बढ़िया है ना? ठीक है? So this is your xy, this is a tangent of delta 1, perpendicular by base, everything go ahead right? So let us put in the values. Is it visible to you? Right. So h1 minus h2 should be equal to d tangent of delta 1. So without forgetting the condition, we are doing for thin lenses, and if delta 1 is really small angle of deviation, then tangent of delta 1 can be replaced as delta 1. So इसको थोड़ा उठा के यहाँ लिखते हैं, ठीक है ना? ठीक है, बढ़िया. So we'll write h1 minus h2 is equals to d into delta 1. From here you can see that h2 has to be equal to h1 minus d into delta 1. बढ़िया ना? There is no particular glare there. So you got a value for h2 that is equal to that much, and now let us put it over here and get rid of this h2. So now in equation 2, if I put it back, I should get something like this. h1 by f is equal to h1 by f1 plus 1 by f2 whole h1 minus d delta 1. Everything clear na? Good. कुछ नहीं कटना चाहिए वहाँ पे. h1 is common, my dear. You can see that delta 1 को हटा सकते थे. Delta 1 can be written as h1 by f1. So let us write one more extra step here. So you'll find h1 by f1 plus 1 by f2, h1 minus d h1 by f1. ठीक, सब कुछ क्लियर दिख रहा है. h1 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 सब गायब. So बचेगा क्या? 1 by capital F equals 1 by f1 plus 1 by f2 minus d by f1 f2. So this becomes your equivalent focal length of the two lenses separated by a distance of d. So once again, I think it's clear, no confusion. 1 by capital F, F represents the equivalent focal length of the lens, F1, F2 are the focal lengths of the lens, minus the distance of separation by the product of F1 and F2. All good? Right. So let us quickly find out and finish it off. What should be the position of this lens? Because this is where the imagined equivalent lens should be there, and this is the distance P1, P2. How much is P1, P2? For that, I need to get rid of this part. Okay, so I remove it. I'm very sure that you guys have noted it down. Alright, you can always pause it and note it down and feel comfortable about itself. So position of the lens, the position of the equivalent lens. The position of the equivalent lens should be where? So that should be this PP2. I want to find out what is this PP2 exactly. How far from the second lens my equivalent lens should have been exactly positioned. Okay. So PP2 by geometry you can see that it is exactly equal to AY, and that you can see that AY is a part of this triangle YZ by AY. So I will write it separately just for clarity. You can see that it should have looked like this. YZ by AY should be equal to tangent of delta. So AY should be coming up as YZ by tangent of delta. Right. So I can write it over here. YZ by tangent of delta. All good. So what is YZ? Let us quickly see that this is YZ. YZ is nothing but H1 minus H2. So P1, P2 should be equal to H1 minus H2 by tangent of delta, small angles of deviation. So you can replace by delta. So delta, if you remember, which I just rubbed it off, okay, delta can be written as H1 by capital F. So let us just do it quickly. Yes, P1, P2. I'm continuously writing P1, P2, but there is no P1. This is actually PP2. So PP2, H1 minus H2, luckily it is all there on the board. You can see that H1, H2 is all about this. D into delta 1. So this is equal to D into delta 1, and this is delta, which is equal to H1 by capital F. Okay. So now let me get rid of this so that it's all clear to you. All right. So we can write something like this. PP2 should be equal to D delta 1. Delta 1. Delta 1 क्या था भाई? Delta 1 is H1 by F1. And what is this? This is H1 by capital F. So hence the position of the equivalent lens should be equal to dH1 by F1 multiplied by capital F by H1. So you get rid of this. So finally your position is crystal clear. It is the distance of separation D multiplied by the equivalent focal length by the first lens's focal length. So hence this is your expression, very much valid for two lenses separated by certain distance. नहीं दिख रहा वहाँ पे? So फिर से यहाँ पे लिख देते हैं. You can write it here also. That is what I mean to say. PP2 should be equal to DF by F1. That's your position, and that's your equivalent focal length of the two lenses in combination. Alright? So I hope you had good time attending my classes today. If you're new to this channel, if you like this channel, if you liked my classes, please do like it, share it among your friends, and do not forget to subscribe my channel for many more interesting and simplified physics classes. Thank you. Have a good day. Have a great time ahead. Bye-bye.